Well, Robin asked me to speak on nanotechnology, and I've looked into that. But I'd like to start by saying one of the problems with climate change, for me as a filmmaker, is that you can't actually see it. And when you film it, if you can find an image that embodies it, it tends to look rather beautiful, which is a slight drawback when you're trying to make a sensible, hard point about it. Science gives us the abstract information to assure us it's happening, but the world around us, certainly in London, certainly in the European countries, seems to remain constant, at least to us as individuals staring into what we imagine is the unknown, or as Donald Rumsfeld put it, the unknown unknown. But perhaps it's what we can't see, the workings of nanoscience and nanotechnology, that can offer us the paths of a way out from our climate meltdown. Now, I've always loved science fiction. Its writers are guided by science, by human longing, and by the readers and my demand for more bizarre stories. First and foremost, they are technology streamers. Sci-fi dreamt of space flight and it came. It dreamt of robots and they have come. It dreamt of cheap space flight, and with Virgin Galaxy, that is upon us. And intelligent robots, and they too are upon us. You can see them on the program QI. Sci-fi films have imagined minuteness in The Incredible Shrinking Man and the vastness of the universe in Kubrick's 2001. And almost as if they're following them, our scientists boldly go where no man has gone before and present us with both hope of what they may achieve and fear of what the impact of their discoveries might be. And those scientists who work with stuff we can't see seem to worry us the most. Whether it's nanorobots or nanoparticles, it's all just too small for us. I once read a story that had a great impact on my appreciation of size. In it, someone in a first-person narrative comes to the end of life and their spirit flies off the planet and into space. As their consciousness sails far up, it looks back to see our solar system becoming incredibly small. Later it looks back and our galaxy has become minute. Finally, the soul flies past the edge of the universe and looks back to see that our universe is contained, but in the flash on a gold ring on the finger of a shepherd standing on a hill. The spirit of the story turned up later as the plot line in the first Men in Black films, where Earth has been given the responsibility of protecting a galaxy that is the size of Gobstopper and is hidden in, yes, a ring. Now, these stories taught me a fundamental lesson about size, perhaps leading me to study pure mathematics and to play with infinity. Our imaginings of size are almost always dictated by our own, so size for most of us tends to be relative. The universe is our idea of infinite, but to a microbe, this room might be imagined as a galaxy. For the Monty Python foot, our universe may just be there to be squashed. Size for Homo sapiens is relative. We understand a cubic, a foot, a chain, a yard or a metre, a kilometre or a mile. But we are really bad at imagining vastness, and even worse at imagining minuteness. Both defy our empirical experience, our ability to control in our minds the idea of size. We can try to grasp vastness by looking into the skies, but very small little buggers are to our naked eye invisible and therefore almost certainly dangerous. And for the last quarter of the 20th century, we saw the rise and rise of the invisible, at least to the naked eye, in the works of nanotechnologists and scientists. Many of their nano developments were hinted at in a seminal book on the nano world published in the 1980s, but before I talk about that, it's perhaps helpful to define what we're actually talking about. I'm a great fan of classical derivation. It pleases me a lot. Nano comes from the Greek and means dwarf. But mathematicians and scientists used to plunder the symbols and words of long past civilizations now use the word nano to mean a billionth part. So we end up with the nanoscale, where a nanometer is 1,000 millionth of a meter. To give you some hold on the idea of the scale, a red blood cell is 7,000 nanometers wide across, and a water molecule is 0.3 of a nanometer across similarly. But scale doesn't actually stop at this atomic level. In size terms, it's possible to go smaller, as small as you like it, actually. So for me, infinity is a two-way endlessness. There can be sub-nano levels of measurement, a millionth part of a millionth part of an atom, whole new worlds of smallness. Whether they're relevant to us or not remains to be seen. But for now, the nano world falls into two distinct areas. Nanoscience, which is the study of phenomenon and the manipulation of materials at atomic, molecular, and macromolecular scales, where properties, and this is important, differ significantly from those at a larger scale. And nanotechnologies, which are the design, characterization, production, and application of structures, devices, and systems by controlling shape and size at a nanometer scale. And we already have nanomaterials, nanomeasurements, nanoelectronics, bionanotechnology, and nanomedicine, and there are many industrial nano applications. And some of these have already impacted and can impact on the environment and could help with the problems that beset us as our climate changes. But nanoscience and nanotechnology are not new. Chemists have been making polymers for decades, and nanotechnologies have been used to create the tiny features on computer chips for over 20 years. And our natural world also contains many examples of nanoscale structures. From one of my favourites, which is milk, a nanoscale colloid where liquid butterfat globules are dispersed within a water-based solution, to sophisticated nano-sized, nanostructured proteins that control a range of biological activities such as flexing our muscles, releasing energy, and repairing cells. And nanoparticles occur naturally. They've been created for thousands of years as the products of combustion and cooking. Exposure to millions of pollutant nanoparticles per breath have been commonplace since our first use of fire. But how does all this nanoactivity impact on or benefit climate change? Can these developments offer an amelioration of the problem and the activities that led to it in the first place? And I'm going to look at nature. I make no apology for that. After all, it runs the planet, and over billions of years has been coming up with solutions to manufacture that are not of the heat, beat, and treat variety, where you start with bulk material, carve it down, heat it up, beat it under enormous pressure, and treat it with chemicals. What you end up with is 96% waste and 4% product. Man is terribly good at this process and has been using it for a long time, with its subsequent deleterious effect on both our planet and scarce resources. Nature, which has been around millions of years longer than us, decided it couldn't, indeed wouldn't, afford such profligacy. It didn't want to wipe itself out. So its processes are mostly virtuous circles of sustainability and efficiency. Now these are being explored through the science of biomimicry, which is a particular passion of mine. It's not biotechnology, I want to stress that. So great is my passion for the area that I went at my expense to talk to Janine Bengis about it in Missoula, Montana. She is the inspirational figure behind bringing together all the scientists that were desperately working within what we now know as biomimicry. She describes it as innovation inspired by nature. And scientists and technologists take processes or materials and explore to see if nature has an equivalent or an alternative. Biomimicry works extensively at the nano level. It is, as you might expect, a powerful friend of the environment and affords us ways to step back from many of our industrial processes that damage the planet. And nature crafts materials of complexity and functionality that we can only envy. The inner shell of abalone is twice as tough as our highest tech ceramic. Spider silk, ounce for ounce, is five times stronger than steel. Muscle adhesive works underwater, sticks to anything even without a primer. And rhino horn repairs itself even though it contains no living cells. And I'd like just to talk about gecko tape, which is revolutionizing everything from carpet tiles to sticking plaster. Making glue is a very unpleasant industrial process, and scientists knew that the master sticker was the gecko. But it was only with the development of optical tools at the nano level that they could finally analyze the gecko's foot. And it's a wonder. Each gecko toe is covered with 500,000 little bristles, and each bristle has a bad case of split ends. So when you look at the whole of the lizard's foot, there are literally billions of tips. If a gecko pressed all of these multi-tip bristles against a flat ceiling, and they all made contact, the stick would be strong enough to support a 120-kilogram man. Obviously the tiny gecko doesn't need all that, but it's better to be safe than sorry, as they say. Nothing is actually smooth. There's always minimal contact between two surfaces that are placed together. So when a gecko places its foot, a very, very small part of those billions of bristle tips comes in contact with the ceiling or wall. But for the gecko, that's more than enough, and he or she won't fall off down onto your pillow as you gaze up at them on the ceiling. Gecko tape has been developed from these observations. It's easy to produce artificially, though you could farm it off their feet as it grows back almost immediately. And it eliminates the need for some old-fashioned glue environmentally damaging processes with a much more benign one. And American carpet manufacturers in particular almost bit the biomimicry people's hands off for sight and use of this product. Their desire to improve their environmental credentials being a high priority for many of those US industries. Another one is Lotus Sand, which you probably know about. It's a self-cleaning building facade paint created by mimicking the so-called lotus leaf effect. To ensure efficient photosynthesis, it is essential that plant leaves are kept clean. Scientists observe that the leaves of the lotus plant are covered in waxy nanobumps. Dirt and dust loosely adhere to these, and when rain falls, the water balls up rather than spreads out, and loose dirt is literally pearled away, rolling the water off and keeping the leaf clean. And the outside of buildings coated with lotus sand are naturally cleaned by the rain. Paint provides a completely efficient natural cleaning mechanism, and the paint itself is easy and environmentally friendly to produce. Biomimicry processes at the nano level also impact on energy production. Nature creates energy through photosynthesis. In leaves, it operates at more than 90% efficiency, producing chemical energy from carbon dioxide and water by using the energy source of the sun. You all know that. Man, on the other hand, has developed its photovoltaic cells using silicon semiconductors. But that process is very costly and typically only works at around 14 to 19% efficiency. Although at Windsor we learned that if you actually take the panels underwater and cool them, it becomes 30% more efficient than that. Biomimicry has led to the development of dye-sensitized solar cells, which mimic part of the process of photosynthesis. A dye-sensitized solar cell consists of a layer of titanium dioxide nanoparticles covered with a molecular dye that absorbs sunlight. Titanium dioxide is used because of its resistance to continuous electron transfer. However, it only absorbs a small fraction of the solar photons, those in the ultraviolet. So the absorption is intensified by the molecular sensitizers of the dye molecules attached to the semiconductor surface. So it absorbs a greater proportion of the solar light. Not only are these DSSC panels much less expensive than conventional photovoltaic cells to produce, they are considerably lighter and much more versatile as they can be incorporated into the fabric of a building to create solar windows, awnings, blinds and roofs, something that's very important in places like Africa. They also use much more environmentally friendly materials. And when we were at Windsor, water was very much an issue, and I just want to mention aquaporins. Aquaporins are naturally occurring membranes within plant cells. They allow the transport of small water molecules whilst blocking larger molecules such as salt. At the moment, scientists are using this principle to try and mimic the hourglass shape of these aquaporins to create a 100% efficient water purification technology. In a world where an inconvenient truth in the hands of Al Gore, as brilliant as that film is, leaves me at least with the impression that we are all inevitably doomed, biomimicry is one of the areas I feel offers us some light, and not only at the nano level. We were talking about sustainable buildings earlier on, but architect Nick Pierce, working with Arup, has built a mid-rise building, the Eastgate in Harare. It has no artificial air conditioning and uses just 10% of the energy of a conventional building its size. This was achieved by mimicking the self-cooling mounds created by African termites. These mounds maintain their internal temperature to within 1 degree of 31 degrees centigrade, day and night, whilst the external temperature varies between 3 degrees centigrade and 42. This produces a naturally cooled, very efficient building, and it's led directly to an impact on the bottom line. Eastgate's owners saved $3.5 million that it would have cost to install the normal air conditioning system. Outside of being eco-efficient and better for the environment, these savings trickle down to the tenants, whose rents are 20% lower than those of the occupants in the surrounding buildings. And to my delight, I didn't know this, Michael Hopkins used precisely this approach. He's an architect I work with, when he designed and built Portcullis House in Westminster. It also has this natural air conditioning system. So whether this reduces the MP's rent, I have no idea. And I've heard more about the palm trees than the air conditioning in that particular house. And one further example, a team in Pacific Northwest National Labs in the US has created a new series of nanomaterials based on metal organic frameworks. They're tiny cages that trap CO2 before it reaches the atmosphere. The cages themselves consist of metal ions linked together with organic ligands, forming a porous network that traps the gaseous molecules. The team combined off-the-shelf chemicals, zinc nitrate, and organic building blocks that serve as the foundation for the new material. These unique molecules have 2 to 3 times the capacity for carbon dioxide uptake as conventional solvents and appear to have extremely high preference for carbon dioxide over other gases. So you could stop any further carbon dioxide at point of release if you wanted to start implementing that technology. I hope you can feel through some of these examples that nanoscience and technology can be of enormous benefit to sustaining us and the environment and help us achieve sustainable, eco-friendly and carbon zero processes that are important if we're going to ameliorate and perhaps heal some of the present damage to the climate. And coming from the media, to my mind, nanotechnology already benefits climate change indirectly by transforming the way we can communicate. Nanotech has put phones and computers in my hands, which as a young man I could only dream of. My first mobile in 1986 was the size of Margaret Thatcher's handbag. And as a student, my first computer, the 8400, would have been the size of this room. Through research and development at the nano level, the modern mobile phone, the iPad, the netbook, give all of us who are lucky enough to have them a power of communication that enables us to social network, disseminate ideas, and importantly, tell people what's going on around us, almost instantly, to anyone, anywhere in the world. The implications of this nanotech explosion remain profound, I would argue, as they are being wrestled with by those governments, regimes, and interest groups who would much rather we didn't talk to each other. But works of the nano variety often get a bad press, some of it originating from a book published in 1986, which was and still is a seminal work on the subject. It was written by Eric Dressler and entitled Engines of Creation, the Coming Era of Nanotechnology, which sounds like a film title itself. In it, Drexler outlines many of the possibilities and benefits to us of the discoveries and technologies that he theorized were to come at the nano level. Along the way, among many other ideas, he posited the idea of self-replicating robots, nanobots, which could be constructed to both engineer and be self-learning. And even as the book was published, he himself has said he was dismissing this idea as needlessly complex and inefficient, and was moving on to advocating desktop-scale molecular manufacturing systems that would be far simpler and more efficient. But there was an almost instant debate led by Professor Richard Smalley, which fed off what Smalley saw as the dangers of Drexler's nanovision and the cataclysm that faced us if this research is pursued. Smalley foresaw the world turning into grey goo, which is a phrase you've probably heard, as the nanobots, self-replicating and self-taught, turned into a sort of atomic-sized Al-Qaeda and took over the world. But at no time was anyone researching or developing such nanobots. This completely unfounded fear was latched onto by governments and the Prince of Wales and led to initial resistance to some forms of nano research and development. I imagine it affected their funding as well, I don't know. When something is so small that you can't see it, and it's beavering away doing something which could affect us, I suppose it's natural to fear it poses an unseen threat. And some things we can't see, such as bacterial viruses, really do pose a threat to us. And it's not helped by the media. Writers of science fiction, this just sounds something very strange to me. Can they come back in a minute? What did that? It's very strange. Writers of science fiction simply love nanotechnology. Star Trek, Town Called Eureka, Doctor Who, and many others have used nanobots or nanotechnology for their doomsday plot lines. But most nano applications are being researched or executed to try and improve our common lot. To rain on this imaginative parade, there is no current evidence that anyone is working on self-replicating nanobots in order to take over the world. Though if American military have their way, and I attended a robotic conference, future wars may be fought by man-sized robots, which they're at present developing to replace their foot soldiers. I'm far more concerned about those robots and their tiny cousins. Nanoscience and technology are also active in the medicinal area, the medical area. A film made in 1966 called The Fantastic Voyage, notable for the presence of Raquel Welch, was the first positive medical nano story that I can remember. Scientists discovered they can reduce a submarine with the people inside to the size of a nanobot, which can cruise the highways of the body to target and repair a gunshot wound in a diplomat who is in some way vital to the future of the world. And molecular machines are now over 50 years on being developed to be inserted into people to treat or to cure illnesses in ways that lie beyond the scope of human-sized servers or physicians. Sadly, they all lack the presence of Raquel. One of my favourites, again from biomimicry, is a needle that can be put under the skin of diabetics to measure their level of blood sugar. Its insertion is painless, and it is based on the design of the mosquito sting. So after Drexler's book, Nanoscience and Nanotechnology didn't take off, and nanotechnologies are helping us cut greenhouse gas emissions even now. It's enabled ultra-thin glass coatings to reduce heat loss through windows, which was talked about earlier today, and nanoparticulate additives are known to improve diesel engine efficiency, resulting in annual UK savings of 2 to 3 million tonnes of CO2. But, as Phil Willis said in 2008 when he was then an environment minister, we are ill-equipped to live with nanotechnology. We lack fundamental understanding of the nature and behaviour of most nanomaterials. We have not yet determined the methods or developed the tools that might enable us to measure nanoparticles or accurately gauge their presence in the air, soil, and water. Most importantly, we know little about how nanoparticles might affect human health or the environment. To address those problems that were emerging from the cloud of unknowing at nano level, there was a major report undertaken and published in 2004 by the Royal Society and Royal Academy of Engineering. It's called Nanoscience and Nanotechnologies, Opportunities and Uncertainties. Reading this report, it is clear many nanotechs pose no threat to us at all. Concerns do centre around nanoparticles and nanotubes that are free rather than fixed within a material and therefore cannot wander if they're fixed. The latter's effect is either zero or minimal. But the risks start in the laboratories, working environments where nanoparticles or tubes are created, even if they are later to be fixed. And in the creation of, for instance, cosmetics which contain nanoparticles in free fall. In particular, there are concerns about nanoparticles of titanium oxides and zinc oxides being absorbed subcutaneously and the effect on the body if this happens. The problem with nanoparticles is that unlike larger particles, even those of the same material, they have a much larger surface area. Therefore, the chemical or the explosive reaction when they come into contact with other material is much greater than their larger kin. Something which is non-threatening at the non-nano level can become dangerous at the smaller level. We cannot presume that any material that is benign at a non-nano level is safe or non-toxic or non-explosive. There's also evidence that nanoparticles can penetrate cells more readily than larger particles, leading to fears that some forms of nanoparticle could pose problems similar to those caused by asbestos fibres. In 2004, the report noted there was still a lot of research to do into the effects, short and long term, of any nano developments. That there was a body of work being done about the effects on us, but almost nothing had been done about the impact on other species, which is a fact I find a bit depressing. The effects on man are being monitored, though. There's an organisation called safenano.org. Yeah, reassuring name, if ever there was one. It's one of the bodies that exists for this very purpose. Much care appears to be being taken with regards to exposure in laboratories and workshops that are developing or employing nanostructures. Each development, as I understand it, is highly monitored. And 5 years after that 2004 report, a large comprehensive study, it's a huge study, was undertaken by the IOM, or Institute of Miners, on behalf of safenano.org. Nano, it's entitled, another great movie title. A review of completed and near-completed environment, health and safety research on nanomaterials and nanotechnology. And it just shows how huge this area is. It goes into great detail, much too much to go into here. But it is on the web for reference and it can be downloaded. These reports, though, tell me that at least we are trying to keep our eye on the ball. But that nano ball is exponentially inflating as the potential of nanoscience and nanotechnology technique is now being realised. And herein lies the danger. How do you keep track of such a large explosion of stuff? The possibility of a toxic free nanoparticle tube slipping through into the environment and roaming unchecked rises in scale. So it's those free nanoparticles and nanotubes that we should be our concern, how they might impact on both us, the planet, and its climate. And there's no point of worrying about the 100 million nanostructures there are on a computer chip, as these are fixed. The issues of toxicity, carcinogenic effects, and the potential for new pollution have to be addressed with the emergence of any new nanoparticle tube in the same way as they are for any scientific development, but particularly for these, and any application of these in small or large number. SafeNano.org has as its prime directive the task of making sure that safety is a priority and is observed by those researching and developing nanomaterials. Our climate changes. There can be no doubt about that. Ice ages, violent swings of temperature, whatever we do, will come and go. Species will die out, habitats will change. Tectonic and volcanic events will have catastrophic and planet-changing consequences. The dinosaurs died out either because they were too stupid to develop the science and technology to spot and deflect an asteroid from collision with the Earth, or, as the Sunday Times would have me believe this weekend, because they farted so much methane, they single-handedly caused a whole global warming episode of their own. That really was the Sunday Times this weekend. And our so-called dark ages were probably precisely that, as a massive volcanic ash cloud literally dimmed European light. But accelerating or distorting the way and pace climate changes has been proved to be ill-advised. It takes us into territory where the rhythms of the planet, the processes, the checks and balances that have been in place for millions of years may not and perhaps cannot cope with. This planet will probably be glad to see the back of us if we don't come to some accommodation with both its and our needs. Nanoscience and technology may play an important part in that quest, but there is almost certainly no magic bullet. But suppose, just suppose, through a vast effort of collective will, where everyone that disagrees decides to act together, we could turn that clock back. Let's dream a little. In the 20th anniversary edition of his book, Eric Drexler posits a molecular nano-engine that he didn't cover in his first edition. This system, he suggests, would address global warming and subsequent climate change. He writes that it could work as follows. Molecular machinery can be used to sort gas molecules to extract carbon dioxide from air. This requires substantial energy because the process compresses gas. But it can be done with thermodynamic efficiency to remove 100 parts per million of carbon dioxide from the atmosphere as a whole, compressing it to liquid density for long-term storage. Storage is an issue. I'm going to digress slightly. We have to come up with some mechanism which looks like a tree, extracts carbon dioxide and pushes it back down to the soil, where it can go through a virtuous circle back up as we need it. But if you could do this, it would require several terawatts of power for 10 years. But this could be provided by solar arrays with a total area of a square roughly 200 kilometres each side. By providing the necessary molecular machinery and dropping the cost of the arrays, molecular manufacture can make it affordable to remove and store the excess carbon dioxide that has accumulated since the first industrial revolution. And that's all I have to say on areas of that.
Thank you for that, because I used to think, when I was younger, that there were two types of people. There were deductive people who took facts and made the correct conclusion. And there were sort of visionary people that created things out of nothing. And I've never really met anyone that did both. But I think Chris is in that category. Any questions?
Chris, very interesting, sadly fairly significantly over my head, but I would like to ask you whether you think nanotechnology is going to have serious effect on the unemployment problems we have in this country.
That's rather like asking me whether Didier Drogba is ever going to be an atomic scientist. I think that raises another issue. Someone said the only way to make your living, this is not my idea, this was in about 10 years ago, the only way that you will make your living in the 21st century city will be through your imagination. I think what has happened is that there has been an ill adjustment to the labour forces that were created by the explosion of activity in the 19th century towards the needs and the ways of financing a lifestyle in a century that no longer needs those processes. The problem is that once you start restructuring societies, you bring upon your head all sorts of political and short-term problems that you would perhaps like to avoid either as a planner or a politician. To my mind, at the moment, our cities are not fit for purpose. We are not fit for purpose. Wayfield Windsor will remember Ian Roberts saying we were designed to eat. Since we've stopped moving, we've invited the problem of obesity. I think societies have to find ways of financing day-to-day activity for their populations, which are original, new, and tap into their imagination. I think one of the problems that actually was brought up by Darren, we were talking in the lunchtime, is that scientists, particularly in the UK, feel divorced from narrative. We have this awful kind of, and I've suffered from this, sitting in the middle of science and arts my entire life, without a real understanding of why they are disconnected. From the idea that scientists are not empowered to tell stories, and storytellers are not empowered to talk facts. And it's really, really sad. I don't think this is true in America. I think I've met visionary people in America from all disciplines. Here, I mean, scientists cling to facts, figures, and statistics. I studied statistics. Statistics are no bloody good at projection, really, because there is a law of diminishing returns. For instance, if you make a movie that makes $400 million profit, Jaws 2 will make $200 million. I can guarantee that. That is a Hollywood model that works 99.9% of the time. Jaws 3 will make $100 million. Jaws 4 will be crap. But what doesn't happen is something new. Because there's a boring financial model that feeds the maw of the corporate giant. To re-socially engineer anything is almost beyond anybody but a charismatic leader. And one of the things that we suffer from at the moment in terms of our problems is a complete lack of charisma in our leadership. I'm not going to knock the French, God love them, but they have just elected the most uncharismatic president in the history of the Republic. Great. Fantastic. He's a man that seems to believe government has its own money, as opposed to its population's money or somebody else's money, preferably the Chinese for a long period. What's that about? So, I've now spent a long time trying not to answer your question, because I have absolutely no idea whether it will. I think if people can just be told the stories about the people who really are caring about this, who really are going out there to try and come up with a way of finding. I don't believe there is a macro solution. There is a lot of macro. I believe the macro solution is the tapestry of micro solutions, in the same way as the city is a tapestry of the village it grew up from. I think people need to feel empowered, to know what the story is, and to be able to act without a financial imperative dragging them back. Now this, I don't know what this makes me politically, probably not going to get in the Palace of Westminster with that. But essentially, yes, if nanotechnology and nanoscience can help create an environment that our children can live in that will allow their imaginations to flourish, which is what I said at the very beginning, actually, because I was mourning the death of my close friend Maurice Sendak. creating a new world of imagination for children. And our responsibility, and I would hazard a guess, there are not many people sitting in this room now, all of them are paying attention, that in 10 years this room will be full, because there will be smoke coming from everyone's chair. The finances won't work, social structures won't work, and something will need to be done. I don't actually believe that can be done by the present governments, because I don't think they think long term. But long term at the moment is 10 years. So the next government, the shit's really going to hit the fan. For all of them. I don't want to be elected in 2015, because whenever you start talking about the exhausting of a finite product exponentially, I as a mathematician know that if you accelerate that exponential use, you are bringing the time when it runs out nearer and nearer and nearer, faster and faster and faster. And the fossil fuels are going to run out. That is incontrovertible. Now, everything we've heard within this, and I'm sorry I know you want to speak of it, but everything I've heard about this addresses 20% of the problem. 20% through biomass or renewables. What the are we going to do about the 80%? Because this is all charming, but unless we address that 80% shortfall, we will be going in our ships and our horses. And actually fine. Great. A life fit for purpose. We cannot expect to sustain our expectations any longer. Our expectations are dead in the water. And all that's happening is they're trying to keep them going. It's like we're doing this. And eventually we'll go under.
To answer your question, Mike, thank you for that. To answer your question,
Obama said that shale gas in America would provide jobs for 600,000 people by the end of the decade. Germany, with its green revolution and its investment in renewables and energy conservation, has already provided jobs for 700,000 people. So there is a model that people ought to be pursuing. And of course, Germany has said, we're not going to double or triple our electricity production. We're going to reduce it by 25%. So in answer to Chris, what happens to the other 80%? You don't need it if you insulate your buildings properly and if you do things in an intelligent way.
Yeah.
Okay? And you've got to control the population.
Will all species self-harm?
We're not allowed to say control the population. We have
but
to make people realise it's in their interest to have a small family.
We as all species have will self-harm.
Thank you, Chris.
Cheers, mate.